Suppose x is a random variable having density fx and h is some given function from R to R. We want to define expected value of hx. Now let's consider some special cases. If hx is just the identity function, then this will reduce to expected value of x. Similarly, if this is x squared, then this will become expected value of x squared and so on. Since x is a random variable, h of x is also a random variable, and so we already have one definition, the general definition from probability 1 course using those supremum etc., which most of you have forgotten I guess, which will give you an expression for expected value of hx. Now that one, for this special situation where you have density, will reduce to a rather simple form. And the simple form is the following. If hx is always non-negative, whatever be the value of x, hx can never be negative, then expected value of hx is given by this integral. Since this is non-negative, so the entire thing is either finite or it is plus infinity. But the integral must always exist. So expected value of hx will be equal to this. Now how I arrived at this formula, starting with that supremum definition which you have possibly forgotten, is something that we will take up near the end of the course when we learn about Lebesgue integration. Now if hx can be positive, 0 or negative, so it can be just anything, in that case we have to be a little bit careful and we will do exactly what we did in our Prob 1 class. We shall define hx plus and hx minus. So basically this extracts all those parts where hx is positive and this extracts all those parts where hx is negative. But because I am putting minus, so it is considering the negative part and folding it up. For example, if this is hx, in that case h plus is only the positive thing. Whenever it is negative, I am flattening it out into 0. And h minus is, whenever it is negative, I am folding it upstairs. So this part becomes this. Whenever it is positive, I am flattening it out. Again here I have negative, so I have folded it up. And whenever it is positive, I am making it 0. In that case, it is pretty obvious that hx is hx plus minus hx minus, and both these things are non-negative random variables. So I shall define expectation of this as, now there may be a problem. If this is infinite and this is also infinite, you will get infinity minus infinity. In that case, I will say this is undefined, but otherwise it is always defined. Maybe infinite, maybe minus infinite. For example, if this is finite and this is infinite, then it will be minus infinity. If both of them are finite, then it will be finite. But if this is infinity and this is also infinity, I shall get infinity minus infinity, and then I will say that this is undefined. So this part you should be able to remember from the last semester. Now all this h plus and h minus business may be a little bit irritating, so there is a special case for which you have a simpler way out. If expected value of absolute hx, which is of course non-negative, if that is finite, then expected value of hx is also finite. This could be negative, positive, whatever. And in this case, you have a simpler way of computing expected value of hx. Expected value of hx is just the usual formula that we used for non-negative case. So you can use the non-negative formula even for hx which can take negative values, provided this extra condition is satisfied. And this is what we deal with most of the time. That is why we use this formula most of the time without caring about that h plus and h minus thing. But if it so happens that this condition is violated, then there is no guarantee whether this integral is infinity or minus infinity or it doesn't exist. Then you have to go back to your h plus and h minus business. I am not going to prove this theorem here because this part we have already seen in prob 1 with proof, and from this coming to this is pretty straightforward. You might try it yourself. Once we know how to define expectation, then we can define all the other related quantities exactly in the same way as we did in our prob 1 class. We have variance, we have the kth central moment, we have kth raw moment. All these definitions are exactly as before. Then we have the very useful property if x is less than or equal to y. So they are jointly distributed random variables. Whatever little omega you take, x little omega is less than or equal to y little omega, and expected value of x and expected value of y both exist. Then expected value of x is less than or equal to expected value of y. So this actually follows from the very general definition of expectation that we have learned in our prob 1. And we have the linearity property of expectation. X and y two jointly distributed random variables such that expected value of x and expected value of y both exist. A, B are any two numbers. In that case, this expectation must exist and this equality must hold. Even in prob 1, we really did not prove it for anything other than simple random variables. The general proof will actually come near the end of this course, but we shall be using this freely. Let x have density f, then expected value of x to the power 4 has this particular expression. Now, I will consider it like this. I shall take y equal to x square and try to find expected value of y squared. You understand, I am actually doing the same thing. But x has density f, so from that I can somehow work out the density of y. And now I can again use the definition to this expression and say that expected value of y square is this. So I get two different expressions, completely different looking thing for what is essentially the same quantity. Is there any guarantee that you will get the same answer? If not, then our definition of expectation has a serious flaw in it. But fortunately, there is no problem. These two things will always match. Indeed, you can write any function of x in this indirect way. So here I first defined x squared and then I squared it. And here I directly raised it to the power 4. And you can write the same function in lots of different indirect ways. Fortunately, our definition is consistent. Howsoever you do it, you will always arrive at the same answer, though the expressions are looking quite different. I am not going to prove it. The proof is somewhat technical, but this is the main idea. I shall give you two problems. The first one says x has this particular density. You have to find expected value of x. And in the other case, it has density given by this. Again, you have to find expected value of x.